Hello everyone. Today is the day 13 of 75 hard research challenge. Yesterday, that is on day 12, I studied how to train large model on single GPU, and specifically I studied something called gradient checkpointing, and I'm going to discuss this today. So let's get started. So let's say you have a very large model with you, let's say a large language model or any specific neural network, deep neural network with you, and you start with, and you have a GPU of certain size, let's say 16 GB with you, and you start with a batch size of, let's say 64, but you get the well infamous out of memory, out of GPU memory error, right? So what do? You reduce the batch size from 64 to, let's say 32, and still you get let's say the same error. So what do? You reduce the batch size to, let's say 16. Okay, now let's say you are able to do a forward pass as well as the backward pass. However, you have noticed on a larger GPU that your model trains better and much faster, like it has a better convergence if you train it on a batch size of 64. So how do we go about it? So what we can do is that we reduce the batch size, but so what we can do is that we can accumulate the gradient over a set of batches and then back propagate only after a certain set of batches have been seen. This can be easily done using Hugging Face libraries, and there is a single flag that you have to pass, and you have to tell how many batches you have to see before you do a backward pass on top of it, right? So this is something called gradient accumulation. However, what would happen if, let's say, you continue to reduce it to from 64 to, let's say 32 to 16 to 8, 4, 2 and 1, but still this also gives you out of memory, or maybe your model is just too large for your GPU, or the GPU is just too small for a standard neural network to perform, right? So you cannot accumulate gradient. It's not a very scalable solution because you're doing a forward pass on one batch and element in a batch, and then back propagating and so on and so forth, right? So what people have come up with is something called gradient checkpointing in this case. So what do? While doing forward pass, we save certain activations at a particular layer to be used during back propagation, right? What do we mean by that? Let's see a particular uh, uh, equation with us. Let's say you have this particular equation, right? And this particular equation can be represented using this computational graph, right? So how do we, what do we do next? So let's see what these two diagrams 1 and 2 show two various forms of how to compute each node in the computational graph. For example, you can first compute x1. Let me zoom in a little bit. You can compute x1, then x2, then x4, then you can compute x3. So at a time, how many nodes need to be there in the computational graph? Let's say all of these take equal memory, then you need to have 4 nodes in the graph before you can compute the x5, right? So this is what they do. Before you can compute x5, or rather before you can release the memory again. Okay, so you have to compute x1, x2, x4, but you cannot release the memory of x1 and x2 unless you before you computing x3, right? So that's what they do. So at max you have to keep 4 elements in the 4 nodes in the GPU memory. So after this is computed, you can release these two, and once these two are computed, you can compute this also. That's what they have done this. So you can say that the requirement here is of 4 nodes, right? But let's say an alternative way to look at it, it would be we can do x1, x2, then before doing x4, we first compute x3. Now because we have computed x3, the dependency on x1 and x2 goes away. So what we can do is that we can release the memory of x1 and x2, and then we can compute x4, and because x3 and x4 are available, we can compute x5. So that's what has been done here, right? So in this case, the memory requirement at max is 4 nodes. Okay, so can we do the same for a deeper or larger model, and is there a better understanding or a better way to do this, right? So let's focus on a deep neural network, a linear stack of layers we have, and we can say that for a chain of n nodes in a computational graph, during forward pass we compute activation on each of these nodes, okay, but and store results in each of these forward passes, and then while back propagating, we would need each of these to compute the gradient till this point, right? So what is the memory and the computational requirement? It is order of n, because you are storing each of the forward computation, and then like you are computing it also, right? But let's say we compute the forward pass, and while computing the forward pass we keep on forgetting these also, right? So what we will have to do is that you compute this, then you compute this, then you forget this, then you compute this, you forget this, you compute this, you forget this, and you compute this and forget this, right? So in this case, what is the amount of memory requirement? Order of 1 so far. But what's the problem with this? The problem with this is that when you are going to compute the loss and do the backward pass on top of it, right? Backward pass on top of it, you will need the forward pass values on this node. For that you have to recompute these again, right? So let's say you have done the backward pass till now, then you need the forward pass of this particular node also, so you have to recompute it all the time, right? So that means that each node, this node is getting recomputed once, right, in the forward pass. Then this node is getting computed twice, thrice, fourth and fifth, and when you add these up, this turns out to be order of n square, right? So that's the problem with this approach called memory poor. Then people have come up with a solution to this, that if you store every square root nth node for a chain of n node computational graph, then what you get is that you get a memory requirement of order of root n, because you are storing each of the intermediate root n nodes and so called, right? So, and computational requirement is order of n, because you are breaking the long chain into parts, and each forward and backward pass is going to be computed once or twice, right? Now let's take another example where you have a resonant model kind of a structure, where you have a skip connection as well as a computation that you want to do, right? Right. So these are the skip connections. You can think of it as skip connection. So in this case, if we remove these nodes, that means we checkpoint these nodes, right? Then it does not help us in any way. Why does it not help us in any way? Because let's say I checkpoint this particular node, okay, and then, but even if I save it, I have to recompute the value of this node, and for that I will need this node, and for that I will need this node and this node. So I have to go till the very back, right? But in the case of, let's say I checkpoint these particular nodes, so this particular node, if we checkpoint, then as you can see, it is breaking the graph, this computational graph, into two parts, right? So such type of nodes are called graph separators, right? So if I checkpoint this particular node, when I am going to do the backward pass on this, I have to recompute only this and this. Similarly, but I do not have to recompute any of this, right? Because this particular thing already has the pre-computed value for this, right? And once I have back propagated till this point, I can continue down this line in a way, in a root n format, right? So this is all there is to this, in a very basic and intuitive and simple fashion, that what we can do in terms of gradient checkpointing. Thank you.